Solving quadratic inequalities in one variable is very similar to solving quadratic equations in one variable, but just like when we were solving linear inequalities using the same methods to solve linear equations, we did have to worry about some extra wrinkles. So these are not quite as easy. You do have to worry about some extra problems here. There are different problems than you have to worry about with linear inequalities, although what you have to worry about there is multiplying both sides by a negative. And when you do that, you have to change the direction of the inequality. That'll be true here too, but we've got another bigger problem to worry about. So the first thing really to do is to find the critical values. Now, what do I mean by the critical values? The critical values are the solutions to the corresponding equation. So if you just write the inequality again with an equal sign and then you solve it, those roots will be called the critical values. So solving this quadratic equation is pretty straightforward. I'd bring everything over to the left-hand side as always, and then if I can factor it, I try to factor it. If I can't, I use the quadratic formula, or perhaps quad on my calculator, or I might even graph it. So now I factor this as x plus 2, x minus 3, and that means that x plus 2 is equal to 0, or x minus 3 is equal to 0. If x plus 2 is equal to 0, that means that x is equal to negative 2. And if x minus 3 is equal to 0, that means that x is equal to 3. So these are called the critical values. Now, a little later on, we're going to look at more complicated equations, and there'll be critical values there that are more than just the roots to the equation. But here, this is it. These are the only types of critical values we're going to have to worry about, which are really roots to the equation. Now, after you've done this, solved a few of these, you're not going to really have to write everything over on the right-hand side like I've just done. What you'll do is essentially all the same steps. You'll bring everything over to one side, x squared minus x minus 6 greater than 0. You'll factor it, and then hopefully you will remember that those factors correspond to roots, and those roots are critical values. Now, what I really want you to get in the habit of doing is graphing all of these. But all you really need is a quick sketch. So if you do a quick sketch, the important things are that if you identify the roots to the equation, you've identified the zeros, where it crosses the x-axis. And this crosses the x-axis in a couple of places at negative 2 and at positive 3. And we know it's facing up because the coefficient on x squared is positive. Now, this is enough. This is completely sufficient. When you look at this equation, what you're really trying to do, if you look at the second row here, what you're really trying to do is find values of x that make the left-hand side greater than 0. Now, how do we actually graph a quadratic? Well, we think about different values of x, and then we calculate x squared minus x minus 6, and that's what we put on the y-axis. That's our y-coordinate. So really another way of thinking about that second row is we're trying to find x values that make y greater than 0. Well, on the graph, the regions of the graph that correspond to y greater than 0 are the regions above the x-axis. So you've got this branch on the left here, and you've got this branch on the right here. So we have two separate areas of our graph where the y values are greater than 0. Now, how do we write this branch on the left? Well, the branch on the left corresponds to all the x values that are to the left of negative 2. In other words, all the x values less than negative 2. And the branch on the right corresponds to all the x values that are to the right of 3, in other words, greater than 3. Now, this form of solution, when you first see it, looks kind of foreign, and if you don't have a graph, you may wonder where these come from. So it's really, really helpful to link it to a graph. Now, let's do this exact same problem, but with the change in the direction of the inequality. So let's try x squared minus 6 is less than x. So we can bring everything over to the left-hand side, x squared minus x minus 6 less than 0. It factors obviously in the same way, x plus 2, x minus 3 less than 0. We know there are critical values of negative 2 and 3, so we can do a quick sketch of this. There's one, negative 2, there's the other at 3. And now think of it this way, you're trying to find values of x that make the y coordinate less than 0. In other words, below the x-axis. Well, that's this region in here, in between the two zeros, in between negative 2 and 3. Now, you can combine essentially two different statements into one. How do we represent this region I've highlighted in yellow? We could say it's all the values of x that are to the right of or greater than negative 2, but they also have to be less than 3. So we're trying to write a statement, a single statement that combines those two. All the x values greater than negative 2 and all the x values less than 3. And you can do that quite nicely by just simply writing negative 2 is less than x is less than 3. Now, here's kind of the rule of thumb I want you to think about. If on your graph you're trying to represent a single region, then you can do that with a single statement, like negative 2 less than x less than 3. But if, as in the previous example, you have two separate regions on the graph, you'll have to have two separate statements. Sometimes students want to combine it, and it ends up either being false, usually the opposite of what you're trying to state, or it ends up being a nonsensical statement. And I'll show you examples of those in class. Also, if you are writing this combined statement, you should write the numbers, the negative 2 and 3, in the same order that you would find them on the number line. So the numbers that are smaller on the left, the numbers that are larger on the right. And that means you're always going to be writing these combined statements with less than signs. You'll never write a combined statement with a greater than sign. It's not that it's wrong, but it just becomes difficult to read unless you do it in a consistent fashion. And that's pretty much it. Let's take a look at a couple of special cases. Let's take a look at the quadratic inequality x squared plus 2 is greater than 2x. So let's bring everything over to the left-hand side as we did before. X squared minus 2x plus 2 is greater than 0. This doesn't factor, so let's try using the quadratic formula. If we use the quadratic formula to find the critical values, we take our coefficients a, b, and c, and we plug it in, and we get minus b, which is minus of negative 2, so positive 2, plus or minus the square root of b squared, that's 4, minus 4ac, well, 4ac is 8. And all of a sudden, and then I divide by 2a, all of a sudden I realize there's a problem here. 4 minus 8, the discriminant is negative, which means this has no roots. So since there are no real roots, it means it doesn't cross the x-axis at all. So what does this look like? It might help if we had a sketch of this. If we sketch this, it turns out this has a vertex at 1, 1, and it is always above the x-axis. Okay, so this point happens to be 1, 1. That's not really all that important, but if you graph it on your calculator, you'll see that it is entirely above the x-axis. So, in fact, any value of x is going to make that original inequality a true statement. You can try plugging in a few. Try plugging in 1, for instance. You get 1 plus 2, that's 3 on the left, 2 on the right, that's a true statement. Try plugging in other values and you'll see that it's always true. So, therefore, x can be any real number. That's the solution to this inequality. What if we had the inequality pointing in the opposite direction? In other words, what if we had x squared plus 2 less than 2x? Well, again, we would approach this by, if we were seeing it for the first time, we'd bring everything over to the left. We would use quad or quadratic formula and realize it doesn't have any real roots. We would sketch it. You get the same graph, and you realize, okay, it's never below the x-axis. There's no value of x that's ever going to make x squared minus 2x plus 2 less than 0, and therefore there is simply no solution. There is no value of x that will make this statement true. All right, a slightly different special case. Let's say we have the inequality x squared plus 4 is less than or equal to 4x. All right, let's bring everything over to the left-hand side. X squared minus 4x plus 4 is less than or equal to 0. This factors, and the two factors are the same, x minus 2, x minus 2. And hopefully you've graphed enough of these to realize what this looks like. It has an x-intercept of 2, but it only has the one x-intercept. And of course, since it's facing up, that means that it comes down and goes back up again, touching the x-axis at a single point, 2. Now, we're trying to figure out values of x that make this function less than or equal to 0. Well, there's no values of x that are going to make it less than 0. It doesn't go below the x-axis at all. However, there is this single point that makes the quadratic function equal to 0, and so that's sufficient. That's at least one solution, and so you get x equal to 2. So you can start with an inequality and end up with a solution that is a single point. That's fine. It doesn't happen all that often, but it is fine. Now, in the book, they talk about another method called critical value testing. Critical value testing is a useful method. However, I think it's unnecessary for solving quadratic inequalities. We'll see it a little bit later on, and we'll use it when we get into some functions that are much more difficult to graph. But for these, since they're so easy to graph, I think you'll find critical value testing actually takes you longer. I'll give you an example of how it works. Let's say we have x squared minus 5x plus 6 greater than 0. We could come up with the critical values any way we like. In this case, this factors quite nicely. And so you can get your critical values of 2 and 3. Now, you just simply take a number line and you plot those two critical values on the number line. When you have 2 points on a number line, you've divided the number line into 3 regions. You then test each of the 3 regions. In other words, you pick any value of x you like that is less than 2. Let's try 0. That's the easiest one. When you plug 0 in, you get 0 minus 0 plus 6 on the left-hand side, and that's obviously greater than 0. So this works. So we accept that. Now, because it's a strict inequality, we can't have 2. 2 is not going to work because we know that'll make the left-hand side equal to 0, and 0 is not greater than 0. And similarly, 3, that's going to be not part of the solution. Then we test a value between 2 and 3. Let's say a value like 2.5. Now, when you plug in 2.5, you get 6.25 minus 12.5 plus 6, which is going to be minus 1/4, which is not greater than 0. So that fails. That does not make the original inequality true. And then you plug in a value that's greater than 3. 4 would probably be the easiest one to plug in. You get 16 minus 20 plus 6. That's 2. And 2 is greater than 0, so that is true. And so you then just take this number line and you translate it into solutions. The region to the left of 2 would be x less than 2, and the region to the right of 3 would be x greater than 3. But, as I just said, I think you'll find it a lot faster. Once you know the critical values, you can just very quickly graph the parabola. In fact, you can think of the parabola as just passing through there. And then you're asking yourself, where is it positive? Well, here and here. And I think that's a lot easier than just plugging in some values. Plus, there's a chance of making a mistake when you plug in values. And so I would suggest leaving the critical value testing until later in the year.